Yes, we can start, I think. So, welcome for the today session. So, I think today is the last session, and thank you so much, Rahim, for your nice ongoing support and presentation efforts to spread new updates on radiation surgery. So, yeah, welcome for today's session.
Yeah, thank you. Thank you everyone for joining this um, the last session of the whole the lecture series on the SRS program. And the previous two lectures were a little bit boring. And if you have missed, then watch on the YouTube stream. Um, it's available online. And this one should be interesting because I'm going to discuss our journey, that how we managed to put up a new SRS program from the scratch. And this one is on the Electra Versa HD platform. And definitely the fundamentals, the preparation, and the validation pathway for any SRS program is equally valid for on the variant side. Although definitely there are differences in terms of the workflow. And because this was done in parallel with the commissioning and acceptance of the exec track as well. So you might see that I might be touching again some of the commissioning path, the way we did, and some of the devices as well, because with this SRS program, we got some of the devices as well. So in the first lecture, as we have developed the whole rationale behind why we need this program, some of the literature we discussed. And I think in the second part, you might, you have missed, you can go and watch the major a substantial amount of time I spent was on really hitting the mark, right? So that was about the Winston Lutz and how to develop the relationship between multiple ISO centers and especially particularly the calibration chain of MV ISO center with the XVI and the exact track. So that was the second part. Um, so again, a disclaimer, and you can just read and pause and read if you want. And the important thing is we are recording. So if you're not comfortable, this is the time you can leave. Thank you. Okay, so so in this part of the lecture, you will see that definitely in any SRS program, the infrastructure, the governance, your access to the multidisciplinary team, your selection of the equipment is crucial. So I'm going to show you some of the equipment we do have. And this part, I think we have spent enough time during the second part of the presentation, and I'm not going to discuss too much here. And the TRS 483 in the first part, in the especially last 20 minutes, I have touched a little bit on 483 as well. And this one, we are going to, again, just to refresh your memories, how we did, I'm going to show you. And one of the critical and the important equipment in our department is really the SRS map check. And that was the new one when we started, and we commissioned that one. I'm going to show you our commissioning results, how we did. The film system was already established in our department, but still I'm going to show you through figures, through diagrams, that how you can establish a film dosimetry program in your department. You don't need really too much, but if you have a license for a software and a small phantom, then it's easy to really establish the film dosimetry in your department. And it's very important, particularly if you are a new department, and then definitely end to end. Before starting any new modality, we need to go in a fashion of end to end using, definitely in this case, we use the Phantom. We call it the Stew Phantom. We started with the CT scan, and they went through every process of where the patient is goes through, and then the audit results I'm going to show you. And then at the end, that was the day where you start uh, treating the patients. All right, so I'm going to touch some of the challenges you can face, especially if you are setting this program in the regional settings, metropolitan, big cities where there is a lack of definitely facilities, and if you need something, you cannot really immediately you can get, right, because you have to really travel a long distances. That was one of the challenge, and this was one of the first program we established in the regional settings, because in metropolitan cities this program is pretty much available in every center. That's the very normal. But for regional centers, this was the new one. All right, so just Linux-based radiosurgery has gone through a long journey, and I think we have discussed that one. But as I mentioned earlier as well, that with the advent of the external imaging capabilities from the third-party vendors, particularly compatible and very good workflows with these kind of linear accelerators, whether it's Varian or the Electra, they have made our life very easy. And because these imaging capabilities have really surface guidance, can do stereoscopic imaging, real timing, trigger imaging. I mean, pretty much everything. So that's these. And in our case, just to be clear, that the imaging system we do have is the exacted dynamic. Just just to give you some of the examples, earlier I mentioned that what you can face really in terms of the challenges you can face if you are setting these kind of programs in regional settings. That, as I mentioned, spare parts. Sometimes if you need a small thing, you need to struggle really to get that part. Otherwise, you have to postpone your whole. So in our case, to reach to the regional, to the metropolitan city takes 5 hours, right? So sometimes, particularly if you don't have on-site engineer, then that's also a challenge. And so some of the workforces, to return workforces, is also a challenge in these areas. Anyways, I'm not going to go into more details. Let's go into the. But establishing this kind of program is very easy if you have a national support. Just like in our case, we do have a national physics support. We do have a national multidisciplinary team, which the doctors sit online and discuss the cases. We do have access, remote access, pretty much on every system to the vendors. Definitely, we do have on-site physicists. So these are some of the things which can make your life easy if you're working in a network. But definitely, this may not be easy for someone who is working independently in a center, in a small institution. So these are some of the stuff you need to you need to think about. Because if you don't have a proper established multidisciplinary program, if you don't have a credentialed RO to discuss a really an SRS plan, right? So how you are going to proceed with the treatment. So these are some of the challenges. And if you don't have a physics access, if you don't have the access to the built-in protocols and the policies, departmental policies, then you need to do everything from the scratch. That was not the case, or in our case, so that was easy for us. All right, so just I'm going to spend some time on the exerted dynamic um, because I have made my life easy by discussing KV-MV calibration in the second part of the lecture, and so we are not going to go into the details, but just a little bit on the exerted dynamic as well. So those who are not aware of this system, So this looks like this. So it has a basically optical cameras, and you have one light projector, and you have one thermal camera. And then on the floor, you have KV sources underground, one source on here and the other side, and one source on the other side. And on the ceiling, you can see there are two panels that X-ray emits from here, and it captures the image of the patient, and you can capture from here. And the same is the case. This is your KV panel source, and then it hits here. Then there is. So both these are orthogonal to each other. But the beauty of taking this kind of orthogonal imaging is that when you give a kick to this couch at any angle, you can really take the image and do the corrections. If there is any sort of run out, either the gantry run out, the couch run out, the collimator run out, it can correct those sub-millimeter displacements. So that's the whole theme. And if you correlate this with the second part of the lecture, you can understand that how come we were able to really minimize the margins around the PTB because of this external imaging. If you don't have this set of imaging, then if you do a cone beam CT at couch 0, run the first arc, and once you give a kick, and then that sort of displacement or the run out, the mechanical run out of the inherently in the system, then there is no way that you can do the correction, right? Because the XVI is not going to work once you give a kick. And we have seen that in the first part of the lecture. So the console looks like this, that once you put the patient on the couch, you will see that it can determine the differential change of the temperature across the body, because you can see this is a partial mask, and you can see here this is different than this, because the temperature is different on the mask than the neck of the patient. So it projects the light on the patient, and the reflection goes back and the sensors capture, and then you can create a three-dimensional map of the patient. And then you do the stereoscopic imaging, and you can simultaneously see that if there is any minor motion of the patient, then you can see the scale is very small, so sub-millimeter. And you can define the tolerances within your during the preparation of the templates for head and neck, for pelvis, for every site, we have particular protocols built in. So the green tick means that the exact track is not going to stop the beam. And if it is not within the tolerance, then definitely it will stop the beam. So that's the whole thing. So it means that you have within a sub millisecond, if there is any movement of the patient, then the beam will stop. That's the whole concept. So stereoscopic imaging, thermal endosurface, and then as a result of all this imaging, it gives you, it calculates the 6 TOF, and then you can just say, you can hit by saying that shift those residual shifts where in this case to the X support, and then it will correct and do the image again, and you move on. So that's the whole idea of using this exact dynamic, that you can do the real-time monitoring. All right. Now, uh, just a refresher again. When we get this system at our site, definitely we get the system along with some of the phantoms. This one is your thermal calibration phantom. This one is called the system calibration fan, and this one is the part of the support. So that's the frame. So the question was that if you have been asked to really calibrate your exact dynamic so that you can use it clinically, then from the second part where I was showing you a chain of the calibration chain, you can see that I was saying that you can heat up this fan, and these circles have a noun diameter, and it can heat up. It takes 10 to 15 minutes. Once you heat up, you put on the couch. Once you put on the couch and you look at the screen, you will look like this. So this will develop a relationship between the surface and the thermal, because this area, the temperature will be different than this area. And this area has a noun diameter, therefore you can build a relationship between thermal to surface. So now the surface to the kV. For the kV, you need this, and it has a noun circles built in with a different density. And then once you take the X-ray, you can develop a relationship between the surface versus the kV, and it will save that isocenter into its memory. So in this case, you can develop a relationship. For doing how to determine the kV, how you are going to determine the relationship between MU isocenter and the exact rate. I haven't put any picture here, but it's simple. Again, you put the ball bearing, do the MV imaging couple of times, give the shifting through the vernier caliper. Once you get enough low residual shifting on the MV, then you can just take two orthogonal images through the exact rate, and then it will save that position of the ball bearing. You call it a small sphere, and we also call it a sphere detection. So it's called a sort of a mini Winston darts. And in that case, you can save the MV isocenter for the exact rate, again using the ball bearing. That's the whole idea. Okay. More in a more elaborative way that you can develop from thermal using the 3D thermal phantom to the surface, which I explained how, and then from the surface to the kV, and then from kV, how you can develop a relationship between the MV. For that, you need software. In this case, we have the Aqua. We take MV images, determine our MV residual, and if this shift is higher, we try to give through the vernier, do it again, and minimize this shift. Once we know that our ball bearing is exactly at the MV isocenter, we will capture two images. In this way, you will able to develop a relationship between kV to MV isocenter. So that's the whole idea. All right. So for how to verify that your exact check dynamic is giving you the right shifting you want. Meaning that the shifts you are getting through your XVI onboard imaging, the shifts you are getting through your stereoscopic imaging, the shifts you are getting through the surface imaging, how you will verify. So in this case, we consider a CBCT shifting as a gold standard, and we will compare the shifts given by the rest of the systems. Okay. Therefore, it's easy to put a phantom, do the CBCT, and note down the shifts. And do the imaging with the exact dynamic and note down the shift and look at the surface readings as well. Those they should be in a correlation. Now the question is that if you are going to introduce noun errors, if you want to move a couch in a certain linear dimension, suppose 3 cm along the positive axis, and then you move the couch, do the CBCT. Definitely CBCT is going to give you that 3 cm in AB direction. And then you repeat with the exact track, it will give you again the 3, and the same with the surface. So in this is the part of the commissioning that you need to verify your system its accuracy by introducing the error. So there is a complete spreadsheet you need to verify, and this way you will be able to find out your coordinate system as well. If you know in which direction you are moving, even you can move the hexaport for each yaw and the roll to your dependent noun value, and then you repeat. So these are some of the checks you need to verify that and the difference, the root mean square value should be very, very minimal for this kind of the comparison. If you compare the exact check and the SGRT versus the CBCT. All right. Uh, Basically, this topic is not the TPS commissioning. Rather, it's a subset of the commissioning, particularly for our SRS program. For the larger field size, the set of the planes are totally different. And I have mentioned earlier that if you want to introduce your SRS program in your department with which you have an existing TPS, then you can't assume that your model is good enough to really give you good agreement for the smaller field sizes. So you have to commission and the equipments as well. So let's see. The first device we got was the SRS map check. So this looks like an SRS map check, and it has a active array of 7 cm by 7 cm sitting in the middle of these acrylic sheets, and it gives you a sort of the dose plan, dose matrix in a single plane. It's not something like ArcCheck, which gives you three-dimensional. No, it's just a single plane. But how you are going to use this system? The first step to do is that you have to do a scan of this phantom. If you have, this is a stereo fan, okay? If you got this with the US stereo fan, which is the full set, and you can move this SRS map check in any direction 360, and you can get any plane you can check. But in our case, this stereo fan was missing, so we built a 3D printed phantom, and we inserted the main part of the detector into the 3D inserted, and we scan. And now you can see this is the basically active diodes are here, sitting here. From there, once you do the scan, you should know the center. You just mark it with your markers outside so that you can define your user origin on the TPS. So you take these wedges back to the Monaco. So this is your how the user interface looks like for the Monaco. And then you just start with the calibration. For the calibration, it has a certain guidelines given here for the map check. Then you, for this case, you define 5 by 5, and then determining the dose for 100 μs at this particular depth, and then note down the values. And while doing the calibration, it will ask you to just put that value. You just deliver, you put your map check on the Linux. In this, you can use this one as well, but just to make it easy, your life. So you put it like this way, 5 by 5, and you, once you radiate, it will ask you to put the value, that 100 centigrade. So this will save as a calibration file, and then you can use it clinically. But before doing that, definitely any detector you cannot straight away use unless you find out its check its new linearity, dose dependency, envo dependency, and all those stuff. So we did that. So these were the results, and you can see the dose rate dependency. Brilliant. It was really brilliant, and you can see up to very small dose rates, the deviation was very minimal. We took the SRS map check central CAX value for noun and 200 μs with varying dose rates, and your results is very minimal. So same the linearity. Ideally, if you put you deliver 150 in this agreement, the difference should be very minimal. And what we did in the same case, that we checked with the clinical examples. I'm going to show you this NatCom plans. We, whenever in our center, whenever we start any SRS program in any center, we do have a clinical plans with the varying complexities, starting with the simple to the very complex, because we have done validation with the films for the Linux, and we know those plans are good enough. And that the person is fine. So we do deliver these plans on the map check as well, and do the gamma analysis at various the DTA criteria. Let's see. And similarly, we did for the angular dependency, and this is something you are expecting here. You can see the worst results are here, 90, because once you radiate, once the linear goes to the 90, you are hitting the array parallel to the beam. So there you are getting the worst results. But overall, everything is very, very good. Don't look at this one. Look at the scale here. All right. So similarly, we did the film, and as I mentioned, that the film program was already existing for the SABR lung and the SABR spine. So um, there was no need to really commission this scanner and the software itself, rather just the calibration process. But as I said in this lecture, I can't cover the film calibration. It's not a simple process. You just cut down the films with certain dimension, starting with the zero dose and then varying doses up to your upper limit. We normally do up to 40 gram, and then you just take those films, scan them, and after loading, you need to create a calibration curve and to see that how it's fitting here, and it will give you the deviation for all those channels. So the same as you can see that once you create a plan, the patient scan, you can convert that plan into QA plan. They create a plan. This is the CIRS score, multi-slice phantom. So the beauty of this phantom is that um, if your PTVs are sitting other than center, meaning that if you have multiple meds sitting across and you have a single isocenter, you can find out the plane in terms of where anteriorly where it is sitting, posteriorly, and then left and right, supine in, and then uh, you can you can create a QA plane here and take the dose planes. Take the dose planes from here to this case was Film Pro QA, Film QA Pro in our case, and then do the measurement using the GEF chromatic HD films. And if you have the measurement dose and if you have the TPS dose, you can overlap them, because while radiating these planes, you can define where is your centering, the mark here, and then you can find out the gamma analysis. So I suppose time consuming, but it's doable. So for any new system, any new center, this is recommended. A little bit, as I said, there was no need for us to really go to full commissioning. Rather, we did a subset. And as I said, that we have national commissioning sub plans, and those plans are starting with the single ISO with a single MET, and then a little bit off axis, one CMO off axis, two CMO off axis, two METs, three METs, and then up to 7 METs, 8 METs, 10 METs. So these varying complexity SRS plans we need to validate and get the results here. So, so our results were very, very good. We were happy. We did the point dose measurements initially as well for the same national NetCom plans, just to get more confidence, because the chamber readings, the chambers are more robust than the diodes, right? Because you can get the central CAX doses from your map check SRS, but normally the chambers are considered more robust. So we did the point dose measurements, and you can see. If you compare the ion chamber measurements with your TPS doses, the differences are very, very minimal. And that difference, as I mentioned, that can get worse if your field sizes are the PTB sizes are smaller and smaller. From there, you can determine at what point in your model fails. From there, you need to put a lower limit that, oh, we have validated these plans up to this much. Below that, you can't really use. So in our case, 8 millimeter is the minimum size. After that, we do really measurements. We can't rely on secondary checks or something like that. We have to measure because those are not being validated. So this is how we define our minimum size for our SRS program. And just to give you a little bit more that how to analyze the plans, the validation of the plans that using the CIRS multi-slice fan. That in the first part, you need to upload both the TPS dose matrix and the plan dose matrix, and then in the second panel, once you start doing comparisons, it can show you if there is any shift given, and we have a certain limit we can accept the shift because really it can optimize. The bigger the shifts is not the good idea that your setup is not good. So we do check the profiles and overlapping, and you can see for such a small field sizes how beautifully these profiles are overlapping, and it can generate you the reports. And we normally do at 5%, 1 mil, and 5% is there because film has its own uncertainties, it says calibration error, setup uncertainty, many uncertainties. It's not like a chamber. So you can, I mean, this multi-slice, these are removable. You can just rotate them, and you can remove, and you can put film in any plane you want based on your the TPS nets. One of the challenges in the SRS program is the access to the MRI scanners. If you don't have any MRI scanners in your own department, particularly is definitely if you don't have a tertiary care center and don't have an MRI, then everyone knows that MRI distortion is the one of the challenges. And because we are relying on the MRI for contouring, we call it the MRI SIM MRI. So we do request our ROs request for MRIs. Just give me a second. All right. So what we did was we got the D phantom. Within our institution, we do have the D fan, and then we took the D fan to that hospital. We did the MRI, and the challenge was putting the those coils because we can't use the head and neck coils for this D phantom, so we were forced to use the pelvis one. So after scanning, we take that same D fan to our CT scanner. We did the CT scan and we fused and we visually checked. Now we have a software as well. At that time, there was none. So we did sort of qualitative analysis and see that it was fine. And on the system, we checked that they have turned on the image distortion option on as well. And there is a TG report as well. For this test, you can go through, and but it has known dimensions. Using the software, you can measure and see everything is fine. Because you know that this kind of distortion, if you rely on the MRI for contouring, then your PTB sizes get messed up. So clinically go live. So before going into clinically treating the patients, we went through end-to-end fashion, even before the audit, because we did the external audit. Before the audit, I haven't put anything here. Before this external audit, we used this Steve Phantom, created the plans, run through end-to-end fashion, through the imaging, through the exact take imaging, through the XVI, in every step. And we were happy. So then we called for the external audit, and the results you can see are they are very small, but you can see we did the film as well as we did with the chamber as well, both the results. Because this steel phantom, you can see when you open this part at the back side, you can remove this small rectangle. Within that rectangle, you can put the films. And other than that, through just above your spinal cord, you can take the chamber as well. There is an insert for it, and we did the iron measurements as well, chamber measurements, plus it has a place for the film. So it went through the whole process of how to treat the patient, cue the shifts as per the exact track with on the different non-coplanar beams, and then the results were very good. So we move on for the treatment. This is because the external auditor was here on site, so they do their own film calibration as well. They were not using ours because ours can be manipulated. There are many ways to do that. So they did independent film calibration. So these were the PTVs radiated, and on the same day, these were just for the reference films as well, and you can see the results, the overlapping, quite good. So semi-spherical arrangement for SRS is the crucial, because you are trying to mimic your plans to the gamma knife, right? So the question was that a big question came that sometimes you have to look for your workload as well as definitely most of the workload that people normally tend to use minimal arcs to save the time as well, because sometimes dosimetrically you may not get that much confidence. So we did a small project as well, and we found that multiple arcs using multiple couch angles can give you a better outcome. So therefore, from now onwards, almost 4 arcs are sort of standard for us. And because this lecture is not covering anything on the planning, but for those who have no experience with the SRS, this is the difference. And I have mentioned this earlier as well, that from the nominal VMAT plans, the SRS is that we nominally we look for the hotspot here and try to give the coverage, but here there is no such concept of the hotspots. This tail is the beauty. But the important thing is that you need to really set your isodose lines in such a way that where this is sitting. And as I mentioned, that there are normally GTVs which are visible and high risk. We make sure that this is happening here. If this is hard spot is really happening somewhere here, and where there is really an OR sitting, and the risk that you can damage that is very high. Therefore, sometimes make sure your heart is sitting inside. So this is, and you must have the built-in templates so that you can say, oh, I'm fine with it. This is how we go through the treatment, pre-treatment quality assurance. Any plans we create, the real plans, we will convert those plans onto the phantom, particularly if you use the film, we create on the film and export the dose matrix, capture it, and then we can compare. Same is the case, we can create for the map check. But normally, currently, we do have the RATCalc, which we used as assessment tool, and therefore we normally don't really capture every plan. Rather, we do the assessment of multiple METs and compare the mean doses given by the TPS and the mean doses given by the RATCalc. If we see there is a big deviation, we note it down. And suppose in this case, this MET was failing because the mean doses were not in good agreement. So we measured. We can measure in different ways. As I mentioned, it's up to us. But normally, the easy way is to use the map check. For delivery, easy. Once your plan is ready, export the plan plus the reference images to your record and verify system as well as your external imaging so that you can create the DRRs. And then on the day of the treatment, using the surface guidance, you will take the patient to the noun ISO center and it will become green, and then you take the images, give the shifts. Once you are happy, treat, move the couch, do the stereoscopic imaging, give the shifts, treat the, and then move on. And in between, you are already monitoring, surface monitoring as well as the thermal. So some of the lessons we have learned today, over the time, particularly when we started. So the first lesson we learned was that if your equipment is not commissioned um, exactly or in ideal way, then you may end up having issues. That just to give you an example, that this is the steel beam. Okay, the steel beam is the center of this couch, meaning that the laser is crossing through the steel beam and the laser is crossing through the center of this couch, the sagittal laser. So meaning this is the ideal center. So this is the exact track, the camera. So when it was not there, this is the eye guide camera. So the eye guide is communicating with your exaport frame, right? So to install this eye guide camera, because of the steel, it was not easy. So during the installation team thought that it's easy to install it off axis, which is fine because once you put it off axis, then you need to give a little bit of the tilt, the angulation, so that you can cover the whole angle. Okay, if it is center, you don't need to give any angle, but if it's off axis, it was off axis. Therefore, the executive guys came and they said, okay, we have to put it here, so we have to do this welding again, and this was put. But the problem was you must have both cameras in parallel so that to get the maximum signal out of your eye guide, because the shifting is going to give through the hexaport frame, and this is working in combination with this camera, right? The electric couch cannot move unless your camera can't see those markers. So that was the problem. And when we check, it has a built-in software in it, and the couch across 90 and 270, we found that one of the marker was out of the field. So we were forced to give a little bit more tilt so that we can cover this one as well. So you can't do the shortcuts. That's the lesson. So make sure that you do is something right. Second lesson we learned was that the exact track, when you get exact track, they will give you this particular frame as well for patient positioning, because it has a built-in mask. To put the mask, there is a proper mechanism here. So they gave us two frames, one for the CT, one for the LINAC. And for LINAC, they know for LINAC, they know that we have to put the frame, and so they have given this part so that you can put the frame here. But on the CT, it was not like this. It was a different, because normally they provide this for the CTs. They are thinking that on the CT we are not putting the frame, but we found that a couple of the patients, we did the scan without the frame. We do put dummy frames on the CT, but because there is no place for us to put, so we found a couple of patients were hitting the frame, and those patients were cancelled because we were unable to put the frame because of the lateral size. The patient was sitting, it was big enough, so therefore whatever you are getting, you have to make sure that you are getting the right thing based on your needs. For Vedian, it doesn't really matter because you are not going to put any frame there. It works differently. And the second lesson we learned was that when you use a third-party software for the treatment, the unique identification which is related to the CT structure and dose plane is very important. And there is a chain which comes from the TPS and it travels through the, in case of the Electra, the mosaic, and then from there you prepare to the exact track, and then you can load the reference data in XVI. So the chain should not break anywhere. So we found that if the RTs are exporting the plane from here to mosaic, and for some reason, if they want to change anything in the plane, they will only export the plane from here to here. And if everything is prepared already, then you are breaking. The exec will not pick up anything. So therefore, any changes you made should come in from here. And those changes should travel from here. Because when you load the patient on the mosaic, it will pick your patient on the exact track. If the UID is different, means unique identification number for that particular set is different than what you have loaded in the exact track, you will not be able to do that. This was something new for us because XUI is not that sensitive. If you make any plan changes, once you promote the fields, you can just only export the set of fields from here to here. Then it's not sensitive. You can do that, but in case of the exact track, it's very sensitive for the safety purposes. And again, the lessons we learn is that the eye guide has its own limitations in terms of the frame, because frame has a certain height. Some of the patients were hitting this part. So we were unable to treat the patients. We were forced to send them to the another center. Unable to, because if the patient is big enough laterally, you can't insert. If they're big enough interiorly, you can't insert. So these are the things, the limitations of the Electa. It's not really the exact trick. And the second lesson we learned was that for this same patient, for this patient, we were reached, physics were reached to assess the plan, and they said, "Oh, we want to use this 3DOF. We instead of just the 3D couch, not the 6DOF." And when I looked at the plan, you can see that the PTV they are treating is just abetting to the brainstem, and there is a very 0 millimeter of the mark difference margin between them. And then for this, what I did, I introduce intentional shifts, errors in the plan, and I calculated and found that if you introduce minor errors instead of treating the PTV, you are going to treat the. So we told the RO that no, we can't use, we can't treat this patient without the 6DOF. So that was the decision. So this was just, you can see 1 millimeter degree and 1 degree rotation. So it's just coming in. So this was a known errors introduced in the Monaco, and it's becoming red. Previously it was green, everything was fine. After this small error introduced, because you can see that this degree of change in any pitch, row or yaw is not going to take into account if you just give the shift through the XYZ. Therefore, it's important that you must have 6DOF. All right, so so the conclusion is that you can set up really a program in regional settings. Commissioning is not a shortcut. You have to go through all this, which we have mentioned through the second part of the lecture as well. ISO chain is crucial because you are introducing a third party. So there must be, it's not only the ISO center of the system itself, rather within the plan you have an ISO center. It should be the same for every imaging system, LINAC, and your structure set, this reference data. I think we have focused multiple times that how come 1 millimeter matters, and I have shown you by introducing the noun shifts in the Monaco, found that if you really create a 1 millimeter shift or a 1 degree of rotation and calculate the same plan, you are ending up treating something else, not hitting the mark. So workflow. Even if you don't follow the workflow properly, it's the same as the dangers of the physics failures. We have found that because, as I said, it different than the ARIA. ARIA is very integrated and easy way to do it. But on the Electra, the workflow is a little bit tedious, so everything should be fine and without breaking any chain. So yeah, that's it. If you have any questions, you can on the floor.
Thank you, Rahim. It was a nice presentation. I think I did not get any questions from the chat box though, but I believe I have some question from my side. Like frequently, I get this kind of question from some of the physicists, like uh, they would like to know the workflow of a center who are really doing SRS from starting from city simulation to delivery. Like, can you just share some of like your workflow, how really you plan your SRS patient from city simulation to delivery, and how really it takes time, or you can say something about the time around also.
Yeah, sure. Let me try to summarize as precisely as I can. Definitely, most of the patients are coming as a reference, right? So once the RO thinks that, oh, this is really a patient for the SRS, and then the ROs arrange for the MRI scan under the same settings as we do the simulation. So once we get the MRI, we schedule the patient on the CT, and from the CT to the treatment, we have 1 week because of the time. If it is exceeding the 1 week, definitely either we have to play around with the margins, because based on the type of the disease, it can your controls may not be representing. So once you do the CT scan, it will go through another contouring station we use it MIM. So MIM workstation where you can do the fusion, and you do the fusion by one art planner. The artists do here planning. So the planners will do the fusion, and it will be checked by someone else, and then it will be referred to the RO. RO will do the contouring, and that contouring, once he is done with the contouring, the patient has to go through the multidisciplinary team for the contour review. Once he is happy, the planner will create the plan, and there will be a planning. If it is very straightforward, it will not go to the multidisciplinary. Otherwise, it will go to the MDT. Once they are happy, then they will create a QCL. You know the QCL in Mosaic, right? So for the
Yeah.
physics, so we do the patient-specific QA. Once we do the patient-specific QA, we another create QCL for our artists so that they can prepare. So on the day of the treatment, there must be a physicist on site, there must be an RT on site. Then you can treat the patient. So within a week, this should happen. But because of any reason, as I mentioned, this is not happening within a week, then normally they increase P2 margins.
So, like a following question, like when you treat this patient, this like let's say when you have SRS plan and it includes some couch kick. Okay, so do you prefer like every art should be checked the CBCT because there is a couch kick and motion?
No, you can't. Yeah, you can't use the CBCT for the couch, right? So that's the whole aim, that you need that external imaging. You
Hmm.
do even we don't use CBCT. We don't use CBCT
Okay.
for the SRS because we have done the validation, right? We've done the validation. We know that there is a sub-millimeter alignment with the CBCT. We have done the CBCT versus the exact rate, because you can do,
Mhm.
initially we used to do CBCT, but there is no need, because your immunization, everything is so robust, your bony layer marks are so clear, you don't need to. Your Stereoscopic imaging is good enough. Surface imaging is good enough. Because once you give the couch, the CBCT is irrelevant. Once you move,
Yeah.
you can't do CBCT because there is no relation, there is no isocenter defined on another plane. It's just on the zero plane, right? But the beauty of the exact track is that you can go any angle, either 92, 70, 30, 45, any angle. You have there is an availability of orthogonal imaging all the time, which
Yeah.
is good enough to give you a sub-millimeter patient positioning. And during that couch angle moment we have mentioned earlier, there is always couch run out. When the collimator moves, there is always collimator run out. When the gantry moves, flexes, there is a movement, right? So, but how
Yeah.
everything is going into cooperate, that's through the imaging.
Yeah. So I believe also you do MRI image scan with the same flat couch like CT simulator, right? Do you have the
No,
same
we don't have.
geometry?
Yeah, we don't have on site, but yeah, our artists do. Yeah, outside.
So another question is like you mentioned in the patient-specific QA, the gamma criteria is the DD is like the dose difference you allow 5% and DTA is 1 millimeter. So is it
Oh
like
yeah,
what is the
that was for the
technical
film.
reason for 5%?
That was the film. As I mentioned, for the
Film, yes, yes.
film, yeah,
Film,
fire.
film.
For the film has its own uncertainties. Yeah, you
Okay.
have two options. We have done within the institution. We have done a qualitative analysis at what point our patient-specific QA protocols are failing, and they are good enough to pick any error. So for the
Mhm.
film, 5%, 1 mil is good enough because for the film dosimetry, for SRS program, the distance is more crucial for us. So therefore 1 millimeter. But we know there is uncertainty on the film, therefore that uncertainty budget is higher. But in case of the SRS map check, we use 3%, 1 mil.
Okay,
Yeah, 3%, 1 mil,
I
because we know
understand.
it's a more robust, and the SRS map check is good.
So we have got a very interesting question. I think it's very nice. Like for commissioning Linux for SBRT or SRS, should all the data be taken into two different detectors, or and to what minimum field? And can we rely upon respiratory position monitoring? There are three questions, I think. One is, should we need to take like all commissioning data with a two different detectors? Number one. Number two is like, what will be the minimum field size? And number three, can we rely on respiratory position monitoring? Number three questions.
Yeah, I have touched this part in the first part of the lecture in the last 20 minutes. That is 100% right that for small field dosimetry, uh, normally the rule of thumb is that you can verify with the two detectors. That's the gold standard. This is a good point. We have to do that. And as I mentioned, for the different for the minimum field sizes, you need to validate and see where your system is breaking down. So in our case, at 8 millimeter is the minimum. Below 8 millimeter, you need to really fine tune your machines in terms of its focal spot and so on in this mechanical accuracy in so many things. So there it breaks. So that's the as a physicist, you are the ones who is going to determine that minimum. Because as I said, we have a net compliance with the varying field sizes, varying um, complexities, and varying minimum to the maximum. Our PTV sizes are starting from 8 millimeter and is going up to 4 cm. So yeah, and the last part I think is the respiratory motion monitoring. Um, no, the reason is that people use the C rate, which is only doing the surface monitoring, but it has a built-in issues because the problem with the surface guidance is that if you're if the PTVs are sitting posteriorly, your imaging system, surface imaging system, cannot see the maximum part of the posterior body. So there is a built-in offsets, noun offsets for those only imaging system. If during the commissioning you know that what is the limitation and you can give an offset manually, that's possible. But the gold standard is to really do the KV imaging so that you can see through the monolayer marks and give the right shape side. But within the limited resources, you can, but again, you have to keep that uncertainty budget in your planning in terms of giving that extra margin. People does that. CRED is very well known and they do that.
Coming back to your that answer, like the commissioning review by two different detectors, like as I understand, like when we get the machine ready to start commissioning as a user physicist, so we have always get a golden beam data reference as a reference, right? So that golden beam data from Electa or Varian, that is there, like when they ship the machine, they in their lab they also measure that machine data by their own detectors, but they didn't share us. They just ask us, please measure your data in on-site and share with us so that we can validate your data. That's how Electa works. So is it not like we are verifying with two ways, like Electa already measured and we also measured on-site?
No,
Is it not like that?
no, you can't rely on any golden beam data. Every
Mhm.
machine is different, and particularly those differences are becoming more pronounced when it comes to the smaller field.
Yeah,
Your models are acting completely differently, right? And I have shown you
yeah.
in the first part of the lecture how come the Electra GPU and the CPU are totally different. If you go into the physics part of it, it's different. So you as a physicist, definitely you will give some initial data to the Electra. They will give you a model for you. And now you are responsible to validate that model they have given to you. Yeah.
Mhm.
If you find any discrepancies at any level, if that model is breaking down for any particular energy or any particular field size, you are the ones who are going to meet with the Electra and say, oh, look, this is happening. And then they will modify, they will give you another. So it's sort of iterative process you have to do again and again. But for the variant side in Eclipse, it's a bit easy because everything is in the hands of the user. You capture data, you enter because below 3 by 3 is not allowing you. You have to tune you need to create just like TG119 and the other more complex plans, deliver them and check. If you're not happy, tune the parameters, either the MLC transmission or the DLG value. So it's an iterative it's independently you can do that for variant. Electra does it's their own way. So it's a bit tricky. We don't know
So
the
you mean to
reason
say
why they
still,
don't.
so you mean to say that it's still with two detector validation is really like is good,
Oh, they
recommended, or
look
you can
for
say.
it's for as I said for even TRS 483 says like this, right? If you're measuring an output factors, it's a good idea to really measure with the two,
Mhm.
just to get some some confidence, right? Because of those small scales, the there is always an error. There is always
Yes.
an error.
So now I would like to share you like a new update. Recently, I was reading one article from AAPM, which is published in the month of May 2026, like 1 month before. So from AAPM, they published a paper like a debate parallel opposed publication. So they mentioned that three discipline collaborative radiation therapy debate, and they focused on medical physics should focus less on geometric precision. and more on biological outcome. So I can see the two group are debating on this, but I know I'm not. I just want to get your opinion on that. Like why
I
AFP and
my answer to you is that you can't get any biological outcome if you don't have the geometrical precision. And I think I have explained in during the hitting the mark that lecture. I have mentioned this, particularly for the SRS. If you don't have the geometrical accuracy, you can't get any biological outcome.
yes. So
It may be
why we
in a
should
different
not?
sense. Definitely, it has been. I don't know in which context it's been, but generally for this
Yeah.
small at this small level, their statement is not right. Generally is fine. Generally is fine. If now look, are you concerned if you are treating a head and neck patients and you have given 1.5 cm of a PTV margin around? This discussion
Mhm.
is useless. All right, we are not talking about that. We are talking about something where we are given a zero margin almost,
Mhm.
and
Yeah.
mechanical systems are involved. Systems are moving around. Systems are drifting. Couch is drifting. Couch is a very huge, heavy object. You have done your everything on couch zero, and when you move the couch, the mechanics is involved. How you are expecting that the motors mechanics involved in the couch is taking you and your run out is zero? It's impossible. So
Yeah.
therefore, geometrical accuracy is very crucial for us,
But
and especially
my
knowing the limitations.
yes. But my point is how a physicist can be really involved to know biological outcome because we really don't follow the biological outcome, right?
I mean, I'm not really a radiobiologist, but there are models, right? Just like the, the radiobiological models were built back in 1980s, right? Since then, definitely, I'm not a radiobiologist, and nor this is my interest. But there must be some new models which can really predict. And I have seen couple, especially for the breast treatments, that with the advent of the VMAT and arc therapy, how the secondary cancers have evolved, and there is a 35% increase because traditionally we use the tangents, right? And literally there was nothing on the other side of the doors except the MSC, the head leakage and any any backscatter from the walls. But now can you see, just to create and sometimes to treat those intermammary glands, we are forced to use the VMATs, and that's the reason there is a low dose on the other side. And there was a paper, and they have done the modeling, and they were predicting. Their prediction was that the secondary cancers, because of the use of the IMRT and the VMAT, there was a 35% increase in the secondary cancers where those patients who are treating with the VMAT. There must be models. That's not my subject. Yeah.
Okay. So thank you so much for your valuable time for making this three session very interactive, very scientific. Like I believe like I have learned a lot from these three sessions, and
That's good enough for
I
me.
and I believe our participants also get some hints and get some know-how about the future of their plan, or if they are ongoing with SRS, they might really get some input and help to improve their practice. So, from the participants, is there any question? Please, you can unmute your mic and ask any question, please.
I think yeah, good. This is good. All right,
Yeah.
Masood, thanks for your time, and thanks everybody.
Yeah, it will be a continued cooperation. It's not the end.
Oh,
Today, maybe the third session is finished, but we will keep arranging this kind of initiative. Okay, I believe.
we will come
Yeah.
with another idea. Yeah, we can share. Yeah. All right, Masood, and all right, everyone.
Yeah. Thank you so much. Have
Yeah,
a good weekend.
we can. Yeah, thank you. All right.